start with a little bit of trivia, which is kind of like the Wats part, where we look at this surprising behavior, try to predict what happens, and then maybe we're wrong or maybe we're right, and then we'll talk about why that happens, and then I'll give a few tips for avoiding bugs that could be caused by unexpected behavior. So first, let's talk about identity. And if you don't know what that means, you will know when we get to the section. So we'll do some warm-up trivia. So let's say we have Python REPL, we type in empty string is empty string. So who thinks that this will evaluate to true? Raise your hand. Thinks true? Cool. Raise your hand if you think it's false. All right, like 50-50, that's good. Or like 10% thinks it's true, 10% thinks it's false, and then like everyone else is radio silence. So it's true. This one was not a trick question. Not surprising. Okay, another warm up. The integer 0 is 0. Who thinks it's true? Yeah, more answers. Okay, who thinks it's false? All right, it is true. Also not a trick question. Cool. What about the empty list is empty list? Who thinks it's true? All right. Some brave souls raising their hand. Who thinks it's false? More brave souls. Or yes. Okay, so it is false. So this is like the first maybe surprising behavior. Some people, particularly people who are new to Python or new to programming. So why this evaluates to false, we will get into a few slides down. Let's do a few more. So empty dictionary is empty dictionary. True? Yeah? Anybody? Okay, so I'm done tricking you, I guess. It's false. Great. Okay, so this one, a few more lines of code. So let's say we have A is a variable, we give the value 256. B, another variable, we give the same value 256. And then we evaluate A as B. Is this true?
True.
True? All right, yep, true. Cool. What if we add one more? So A is 257, not 256. B is 257. What is A as B?
False.
False, yeah. What is going on? You add one and then like his works differently. No, that makes no sense, right? Quick note, I am using CPython here. The implementation details are important for this example in particular. So what if we define A and B on the same line? We set them equal to 257, and then we say A is B. What do you think? True? False?
True.
True! Yeah, so important. There's even a blog post about this that you should read, this particular example. So like, what is going on here? This is really bizarre. So it turns out that in the CPython interpreter, integers between -5 and 256 are stored and initialized in an array, right? So we have like instances of the integer objects already stored between -5 and 256. So when you say A equals 256, you're not creating a new instance of the integer class. Instead, you're saying, I have this variable named A, I'm going to point it to the 256 that already exists. And then you have B, and you're pointing it to the exact same object in memory, so that's why A is B is true. Right, so here they're the exact same object, and is tells you whether they're the same object in memory or not. So if we have 257, we have to create a new instance of the integer class, the value 257, store that in memory. When we create the variable B, we create another instance of the integer class with the value 257. And those are two different objects in memory, so A is B evaluates to false. Another way that we can look at this is with the built-in ID function. So in CPython, this function will tell you the address of that object in memory. So if it's the exact same object in memory, the ID, or like if A and B are the same objects, then their IDs will be the same. Here, they're not the same. But if you define them on the same line, their IDs are the same. So some tips to avoid this causing bugs in your code are when you're comparing values, use equals instead of is. Exceptions are, I usually use is when I'm checking to see if a variable contains object none or not, or if I'm writing tests to test for identity. Okay, so we talked about identity. Now let's move on to mutability. And then after that, we'll talk about scope. So let's example. Let's say we want to create a list. In this list, we're going to store our favorite things, right? Our favorite things are cats and dragons. And then we want to try to make a copy of this list. And we want it to be like a temporary copy, and maybe one day we want to add another thing to our favorites, but we're not sure if it's going to stick, so maybe we want to revert back to the old list. So we don't want to actually modify the faves list. We just want to modify the temp list. So we say temp.append rainbows. Easy warm-up question. What's the value of temp? It's like pretty easy, right? It's cats, dragons, and rainbows. That's how it works. It's a surface level, right? But then, what's the value of faves? Same thing. Yeah, exactly. Cats, dragons, and rainbows. So why does this happen? We wanted it to only be cats and dragons, not rainbows. So when we define faves and we create this list object, we have this chart over here that is a figure representing the object in memory. We have faves, we point to that object. So then when we say temp equals faves, we're basically just creating an alias that points to that same object, that same list in memory. So then when we append rainbows to that list, we're modifying the only list that exists in memory, and it just happens to be that two names point to it, so faves also get modified. So tip to avoid having bugs that are caused by this is to know what objects in Python are mutable, which are not. Most common mutable objects that we use are lists, dictionaries, and sets. And also another tip is to make real copies. So you can make real copies by using the slicing index or by using the built-in list function, which will take any iterable, go through it, make kind of a shallow level copy of the iterable. But I call these shallow. So what does shallow mean? Essentially, we could implement these things kind of like creating a new list temp. And then for each element in faves is what we wanted to copy. We iterate through each of those elements, and then to temp, we have our new list. But what if element is a list or something like mutable object? We don't make a copy of element. So to make this a little bit more concrete, let's say we have the example faves. And faves is now a nested list. So the first element of faves is a list holding our two favorite things. So then we try to make a shallow copy of this list using the slicing syntax that I have in the previous slide. And then we append rainbows to the first element of our list. So then what is faves now? This is basically the same example what we did last time, but now we have nested lists. So how do we solve the problem where we have arbitrarily nested lists and we want to make a copy of the object? So this is where we can use deep copy. Now, like for what it's worth, I don't think I've ever actually practically used this in like a programming problem that I was solving for work or something, but it's there if you want to play with it. So there's this module called copy. In it, there's a function called deep copy, and that recursively goes through the object that you pass to it and makes it a copy. Okay, so one big part of mutability, and one reason why this is important and has probably caused a bug for you in the past, is using mutable default arguments. So let's say we want to create a function, and the function is called append cat, and it takes a default argument, or a parameter called L, the default value of the empty list. And in this function, we do something super simple where we append cat to the list, and then we return L, right? Exactly what it says, we append cat. So when we call this once, we get some pretty expected behavior, cat, right? A list with one thing in it, cat. What happens when we call it twice? Yeah, more cats! So why does this happen? It's kind of weird. It would be reasonable to assume that when you define the function append cat, or rather, when you call the function append cat, Python will check, did you pass it a list or an argument or not? If you did not, then it'll say, okay, well the value of L then is the empty list, creates a new empty list for you, then uses that. But that's clearly not what happens, right? It only creates an empty list once, and that's when you define the function. So what's another way that we could look at this? So in Python, functions are objects, and as a result of that, they have attributes on them, and it's super fun to play with attributes on a function. call append tab the first time, then we can look at func defaults, and we see that that has changed. One thing that's interesting about this is that tuples are immutable, tuples are immutable, but they can contain elements that are mutable, like lists, like we just showed here. We changed that list that was in a immutable object. All right, so just for fun, let's see if we can change this list from outside the function. So what we're going to do is use this underscore character in the REPL that just contains the value of the last previously executed statement. So here what we're doing is we're like, okay, give me that tuple, and let's look at the first element of the tuple, and let's append drag into it. We're going to see if we can do this. So it doesn't throw an error, and then we'll try calling the function append again. And what do you think we'll get? Yeah, cat, dragon, cat. Which is awesome. So you can change attributes of the function from outside of the function, which is a really fun thing that you can do to learn.
This is called jobs.
Okay, so a tip to avoid bugs caused by this is using none instead of an empty list. So then the first thing that we would do in this function is check to see if L is none. If it is, then we'll just create a new empty list for L and then move on with our function. Another tip, we can take advantage of this of sorts. So let's say we were like hackers in the Harry Potter universe, and we needed to write a function that would sort students into houses at Hogwarts. So we define a function, and we have this really slow sorting algorithm. It takes a really long time. So what we want to do is try to make sorting a student faster the second time is keep a cache. So we can do that using mutable default arguments. So we'll define this function called sorting hat, and it'll take two parameters, or two arguments, student and cache, with the default value of an empty dictionary. And recall the dictionaries are also mutable objects. So the first thing that we'll do is check to see if the student is in the cache, meaning we've already computed the value for the house for the student. And we'll just print in basically a logging statement that tells us that we use the cache and then return the house that was stored in the cache. Otherwise, we will compute the house using this slow algorithm, and then add the student to the cache, and then return the house. So the first time we sort me, luckily, this was totally random, but the first time we sort my name, we get Ravenclaw. Second time we use the cache, we get Ravenclaw. It was faster, didn't you notice? But the cool thing about this is we can look at the func defaults, the sorting hat, and if we were a malicious hacker in this Harry Potter universe, and you didn't want to be Ravenclaw, I could just go in here, I could change that value, then put the sorting back on, and I could go into whatever house I want. It's really cool. Okay, last section, scope. I'm running a little short on time, so I might go a little bit faster. Okay, so let's start with an example again. We will create variable name A, give it the value 1, then have the simple function foo that just returns A. So when we call A, what happens? Who thinks that this will just return 1 and everything will work? Who thinks this will throw an error? Cool. No error, 1. So how does that work? Namespaces. Namespaces are magical. Basically, they're dictionaries that map the names of your variables to the values that those variables hold. And so what happens here, there are a few different namespaces running on. There's the locals namespace, which is a dictionary mapping the variables that are inside your local scope, inside foo. That's anything that we would have declared 4 spaces inside the function, right? So what happens when you use a variable name inside the function is it first looks at the locals, sees if you have created that variable there. If not, then it'll look at the globals. That's where we created our variable A. And then globals is at the module level. And if it's not there, then we'll look in built-ins, which is where we get locals and global functions, and then also the list function that we used before. So if we go back to our example, Okay, who thinks it'll throw an error? You're right. Anyone know what type of error?
Unbound name error. Oh.
Unbound local error. Yeah. So local variable A reference before assignment. So what does this mean? There's this quote in the Python FAQ that says, when you make an assignment to a variable in a scope, that variable becomes local to that scope. So what does that mean? So back to our example, incrementing A is very similar to saying A equals A plus 1. So if we look on the left side of this, that is an assignment statement. And because we're assigning a value to A in a scope that is local to foo, that means that now A is a local variable with respect to foo. So then on the right side of the equal sign, we have A plus 1. So we try to evaluate this expression, and then when we look up, we know we're supposed to look at locals because we've already determined that A is a local variable, but it's not, there's no value for A there, so that's why we get the unbound local error. A tip to avoid this, I guess, avoid the error, is to use the global statement. But not recommended. Better tip, don't use global instead.